Scientists just built a quantum sensor that could detect dark matter. Source: Imperial College London research published in Nature. For decades, physicists have searched for two of the universe's greatest mysteries: dark matter and ancient gravitational waves. We know both should exist. The evidence is overwhelming. Galaxies rotate as though they're surrounded by invisible matter. The universe itself appears to contain nearly 5 times more dark matter than ordinary matter. If you like my videos, subscribe my channel and press the bell icon to turn notifications on, so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. Comments are welcome and open for discussion. And according to Einstein's theory of general relativity, violent cosmic events should send ripples through spacetime itself, gravitational waves traveling across the universe at the speed of light. We've already detected some of those ripples: the collisions of black holes, the mergers of neutron stars. But scientists believe an even older signal may still be waiting to be found. Tiny gravitational waves created just moments after the Big Bang. The problem is, those signals are unimaginably weak. They're so faint that even our most advanced instruments can easily mistake them for random noise. Imagine trying to hear a whisper during a rock concert. For years, physicists have wondered whether quantum technology could finally solve that problem. Now, researchers at Imperial College London have demonstrated something remarkable. They've built a prototype quantum sensor that can recover hidden signals, even when every individual measurement appears completely overwhelmed by noise. It's an important milestone toward building future detectors that could reveal dark matter, and perhaps even echoes from the birth of the universe itself. To understand why this breakthrough matters, we first need to understand one of the biggest challenges in modern physics: detecting extremely small signals. Every scientific instrument has noise. Cameras produce grainy images in low light. Microphones pick up background sounds. Radio receivers detect static. The weaker the signal you're searching for, the more difficult it becomes to separate it from everything else. Sometimes the noise becomes so overwhelming that the signal simply disappears. At least, it appears to. This is especially true for experiments exploring the quantum world. Among the most sensitive scientific instruments ever developed are devices called atom interferometers. The name sounds complicated, but the basic idea is surprisingly elegant. Instead of using mirrors or lenses to measure light, these instruments use atoms themselves. Scientists cool atoms until they become incredibly slow. Only a tiny fraction of a degree above absolute zero. At those temperatures, the atoms begin behaving according to the strange rules of quantum mechanics. Lasers then split the atoms into different quantum paths before bringing them back together again. When the paths recombine, they produce an interference pattern. Tiny disturbances, even those smaller than the diameter of an atom, can slightly change that pattern. By measuring those changes, scientists can detect incredibly small motions, tiny changes in gravity, and potentially even completely new forms of physics. Future atom interferometers could become some of the most sensitive detectors ever built. They may detect invisible dark matter fields passing through Earth, or observe gravitational waves with frequencies beyond the reach of today's observatories, like LIGO. But there has always been one enormous obstacle: the laser itself. Every atom interferometer depends on extraordinarily stable laser light. Unfortunately, no laser is perfect. Tiny fluctuations inside the laser create what's known as phase noise. Ironically, that unwanted noise is often far stronger than the incredibly subtle signals researchers are actually trying to detect. Imagine trying to measure the movement of a single grain of sand while standing inside an earthquake. The instrument works, but its own internal disturbances hide the very thing you're trying to observe. For years, physicists believed they knew how to solve this problem. The idea was simple in theory. Use two identical atom interferometers, located some distance apart, both controlled by the same laser. Since both instruments experience exactly the same laser noise, scientists should be able to compare their measurements, subtract the shared interference, and reveal whatever real physical signal remains. The concept has existed for years, but there was one problem. No one had actually demonstrated that it works under realistic experimental conditions. That's exactly what the Imperial College team set out to test. They built a tabletop prototype using two separate clouds of ultracold strontium-87 atoms. Both atom clouds were measured using the same ultra-stable clock laser. Then the researchers deliberately made the experiment far more difficult. They intentionally injected huge amounts of extra laser noise into the system, much more than would normally exist. The goal was to simulate the conditions expected in future large-scale quantum observatories. The result looked disastrous. Each individual interferometer became almost useless. Its measurements appeared completely random. The interference patterns vanished beneath overwhelming noise. If researchers had examined either detector by itself, they would have concluded that the experiment had failed. But then they compared both data sets together. Something extraordinary happened. Oh, the hidden signal suddenly reappeared. Although each detector individually looked like meaningless randomness, their shared information allowed the unwanted laser noise to cancel itself out. What remained? Idan and Nessie was soon about what detector is. Was the genuine physical signal the researchers had been searching for? Even more impressively, the final measurement reached the fundamental precision limit imposed by quantum mechanics itself. In other words, their technique performed as well as the laws of physics theoretically allow. The team wasn't finished. To make the experiment even more realistic, they introduced an additional oscillating signal into the system. This artificial signal was designed to imitate what a passing gravitational wave or a dark matter field might actually produce. Once again, each individual detector struggled to see it. But after combining both measurements, the signal emerged clearly. The experiment had demonstrated something physicists had hoped was possible for years. Even when individual quantum sensors appear overwhelmed by noise, their combined measurements can still recover hidden information. That breakthrough could fundamentally change how future quantum observatories are built. Why is this so exciting? Because the universe is filled with signals we've never been able to observe. Current gravitational wave detectors like LIGO are incredibly sensitive, but they operate within a limited frequency range. Scientists believe many important gravitational waves exist outside those frequencies. Some may have formed fractions of a second after the Big Bang itself. Others could originate from entirely unknown cosmic events. Atom interferometers may eventually allow researchers to explore these hidden regions of the gravitational wave spectrum for the very first time. Dark matter presents another equally exciting possibility. Despite making up roughly 85% of all matter in the universe, no one has ever directly detected a dark matter particle. Some theories predict that dark matter behaves not as individual particles, but as invisible quantum fields stretching throughout space. If one of those fields passed through Earth, future atom interferometers might detect the tiny disturbances it produces. In effect, scientists could observe something completely invisible simply by watching how atoms respond. This research is part of a much larger international effort. The Imperial College prototype belongs to a project called AION, the Atom Interferometer Observatory, and network. Researchers hope to scale these ideas into much larger facilities spanning hundreds of meters, or even kilometers. Similar collaborations are already underway with the MAGIS project at Fermilab in the United States. Scientists are also proposing an even larger experiment at CERN called AICE, the Atom Interferometry CERN experiment. If built, it would become one of the largest quantum sensing experiments ever attempted. Instead of smashing particles together like the Large Hadron Collider, these facilities would use quantum sensors to explore entirely different questions about the universe. Questions involving dark matter, gravity, and perhaps even physics beyond the standard model. It's important to remember that today's experiment remains a prototype. It hasn't discovered dark matter. It hasn't detected ancient gravitational waves. What it has done is solve one of the biggest engineering challenges preventing those discoveries. The researchers have shown that a key noise cancellation technique actually works under realistic laboratory conditions. That may sound like a small step, but throughout the history of science, major discoveries often begin with advances in measurement. Galileo improved telescopes before discovering new worlds. Better microscopes revealed bacteria. More sensitive radio receivers uncovered pulsars. Sometimes, the greatest breakthrough isn't finding something new. It's building an instrument capable of seeing what was always there. And if these next-generation quantum sensors continue to improve, they may soon allow humanity to observe parts of the universe that have remained completely invisible.